All right. Good morning, everyone, or good afternoon if you're on the East Coast. This is Brian Mongkolpoonsuk, Customer Success Manager here at KETIV Technologies speaking. And this is the 69th Fusion Friday is what we used to call it, but Autodesk Virtual Academy for Fusion 360. It's been about 4 years now since we started these Friday webinars. So thanks for joining me along the way, joining us along the way. If you've sat in on our first ones. Yeah, this topic, static simulation, covered it 4 years ago and had about 19,000 hits on YouTube. So I figured it'd be a good topic to cover again, not only because a lot of updates have happened since then, but also because I've been talking to customers regarding different types of static simulation. And then we also have an ANSYS advanced simulation experts on our team who was able to give me a lot of great advice to share with you guys on this webinar today. So thank you so much for joining, and let's go ahead and dive right on into it. So if you have used, I'm going to actually ask a poll here. So let's go ahead and launch a poll. And the poll question will be, if you've used static simulation before, was force the only load type you are familiar with? So it would be yes, you have used force before. No, you've used other loads as well. Or no, you've just never used simulation. All right, I see some answers coming in. 60% so far have voted no, they've never used simulation. 20% says no, they've used other loads in addition to force. Looks like another vote just came in for no, they never used simulation. And then one voted for yes, they just used force as the only load type they've experienced with. Let me see. I can go ahead and share that result there. Pretty sure you can see that on the screen there. So yeah, that's the class today. That's who's in the audience. So I'll go ahead and stop sharing that. All right, so the agenda today, if you go into the simulation environment inside of Fusion, you can see the structural loads that you could apply. Not only is there force, which we've shown in the past, but there's also pressure, moment, bearing load. We're going to go into all those today, besides remote and moment. So you can definitely skip through it when this is on YouTube in the future. There'll be some timestamps for that in case you need to reference this later on if you were trying to use some kind of load like this. And then at the end, we'll be talking about mesh best practices when you have different shapes like cylindrical shapes, how to manage your meshes. And then also talking about like how much is too much meshing and when you can disclude a mesh and things like that. So that'll be towards the end here. So we'll go ahead and dive right on into it. So the first example will be a quick warm-up example of a regular force application. So let me go ahead and create a new study here of static stress. And a little disclaimer, I am putting in most values are going to be steel objects. I'm going to focus more on the constraints, loads, and meshes in this webinar rather than the actual stress that I'm applying to it. And you'll see what I mean by that in just a moment. But first, let's go ahead and take a look at the constraints. So this is just going to be a wall shelf where we apply a load onto this face here. So I'll go ahead and give it some fixed points, very straightforward, and go here to apply the force load of, let's change the units to maybe 200 pounds of force here. Very straightforward. Hit solve. It's going to solve locally. You could do it on the cloud as well, and then you're off. So this is the first one. I covered this more in more detail in the previous webinar of 4 years ago. Oh, just went behind the screen. This one right here. So definitely go check this one out. I'm going to go ahead and post this in the chat room so you have visibility to that. Here we go, copy, and let's paste that for everyone to reference. And that was with the bike fork crown simulation. So this one gave us a minimum safety factor of 9.37. We just want to make sure it's higher than 1 roughly here. The higher, the better. But then if it's too high, it might be over defined or over designed in this case. So you could definitely cut back some weight here. And then we can see some of the stresses that are being applied to the edges there. In this case, it looks like I didn't simplify this, because if we look at the meshes here, there's a lot of detail going on here, 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 and there. So what we can do is go back to the simplify workspace, remove some of these features, and then it can calculate less. And this is more critical when you're working with very large simulation models. You don't want to sit there for hours on end waiting for this to finish. So what we're going to do instead, is we're going to, let me undo that because I got rid of my holes too. Unselect those. There we go. So we're going to go ahead and leave it simple like that, and then we'll calculate this again. So that'll be a basic application of a regular force. Next, let's go ahead and dive into, see what the next one is here. And there we go. Let me pull it up. Would be pressure. So let's go ahead and go over to this gas tank here. I've created this floor surface because if I were to fix this part, the stress or the force that I'm putting onto a fixed point will pretty much not move. So that's why I made a floor surface here. So then when I do apply the force or the pressure, it's going to go ahead and expand more naturally there. So go ahead and hop over to the simulation workspace. Again, these are all static stress simulation loads that we're applying today. We'll create the study, and then going from left to right, simplify. This is already as simple as it gets. Structural constraints, we'll go ahead and fix the bottom of this platform. And here's where, if we were to try to apply a load, if we're going to try to apply this force, I'm going to click and hold my left mouse button and select the interface. Whatever force I'm applying, it's going to go, you see the selection of the cylindrical face there? It's going to point to or it's going to pull everything that I selected into the left direction. That works fine for this surface over here. Like that works fine there. But this surface over here, we actually want it to point normal to that surface, whereas it's actually pointing this way as well. It's also pulling the top one going here, as opposed to, going somewhere like that. And this one is the bottom surface is going left as well. So everything is going left where we want it to go normal to, or outwards in this direction from the center. So that's why you don't want to use force in this scenario. And that's why we would want to rather use pressure. And then this gives us different units. We no longer have newtons and pounds force. We have PSI and pascals. So if we put in a value there, then we can, let's see what it's telling me to pre-check. Oh, contacts. I need to calculate the contacts between the two here. Oh, and then also before I hit solve here, we want to make sure that these outer parts of the gas tank is being selected as well. So we need to go in that direction and go out in that direction. So it's going to be a normal application for a pressure representation. I'm going to go ahead and post this in the chat room as well. This is from the Autodesk website itself, where it shows you applications and when to apply each force. So in this case, it's a uniformly distributed on a defined area, and it's always normal to, and that's exactly what we're looking for right now. So I'm going to go ahead and post that in our chat room as well. There you go. And then you can look at that as we go along here. So after we apply these forces, we have our constraints, we have a green pre-check there. Let's go ahead and solve this. All right, and I want to just make you aware that it's not going to be looking like it's going to explode like a balloon here. If we go to the deformation scale, we'll go to actual. That's what it's actually going to look like, which is not going to be expanded so hugely. This is more exaggerated, just to help give us an idea of where the forces are. And what I like to do is leave the exaggerated, but I can drag this legend here so then we can see where the most stresses are. And it's mostly in the middle there, and then it slowly creeps its way outwards. So if we were to apply any more reinforcements, it would be towards this area here. But the safety factor is pretty high, so we don't have to worry with the boundary conditions we gave it, so we don't have to worry about making it thicker there anytime soon. So yeah, that's an application of pressure. I'm just going to go through each one of these pretty briefly, and if you have any questions, definitely put that in the chat room. But we have a couple more to go into here, so let's go ahead and hop on to the next one. The next one's going to be moment. So let's bring up a familiar old example here. So here's a bike foreground where last time, 4 years ago, we applied pressure or a force actually onto this cylindrical surface here and fixed the bottom two surfaces there, as if the biker was putting a lot of weight from themselves onto the bike fork crown, which is this piece here. So let's go ahead and now simulate a moment for this, a moment as in, or for torque, where this inner part or the handlebar will be twisting very rigidly, very roughly, as opposed to putting force down onto it, we'll be twisting this instead. So if we go to, it's already simplified just to save our time here. If we go to our structural constraints, we can go ahead and fix the bottom two faces. And then to add the load, it's going to be moment. And this will simulate the action of torque on our model. So we'll go ahead and apply it there. And it's already facing the angle that we want, which is perfect. And then we can go ahead and apply, I don't know, 100-pound force per inch there to it. And then after that, let's go ahead and generate contacts for anything closer than 0.1 millimeters, I think it was, will be considered kind of not glued, like almost glued together essentially. And then we'll go ahead and solve for this, and we could see the results of a moment applied to our fork crown. Everything's done locally so far. I'm not sending anything to the cloud, just because it's sometimes actually faster to do it locally than to send everything to the cloud. Okay, so again, this is the actual, this is the adjusted. We can change this factor, say this is high again. We can change the this to stress so we can see it more visibly here of where the most stress is applied. We can go ahead and animate this. You can see the twist and how it affects the rest of the model. And then we can see where the most stress is being applied. And it looks like it's actually to the handlebars pole itself. And at this point in particular, looks like there could be some reinforcement done here and here as well. But the majority of the stress is going to be in the handlebar itself, or the pole for connected to the handlebar itself. All right, so that one is moment. Let's go ahead and take a look at bearing load, shall we? So if you have a washing machine, or if you hand wash clothes and you need it to dry, here's a design I made of a line drying clothing hangers, similar to something we worked with the customer where they had an application where they needed to simulate how much weight this hanger can hold. And you can, as you can see here, this steel rope goes through the centers of this, or into the holes of this. And let me go ahead and hide some of these bodies here, so we could take a closer look at this guy. So as you can imagine, there's going to be force applied to this face here. And similar to the, let's go ahead and go to the simulation environment. All right, these guys came back. It's because I only hid them from visibility. Let's go ahead and go to simplify and remove these. You have to hit remove and not hide because they still think it's part of the model. So you have to go to remove. So let's go ahead and constrain the bottom face first, and then we can talk about loads. All right. And then now that we constrained the bottom, let's go ahead and apply a load here. So we wouldn't want to apply a force for the same reason as the, sorry about that, for the same reason as the, or a similar reason as the tank, the gas tank, because in this case, if you imagine the gravity and clothes hanging from that line pulling down onto this model, it's not going to really affect, it might not even touch, the rope might not even touch the surface up here. It probably only touches the surface down below here. And with the way the rope behaves and the gravity and the force behaves onto this cylindrical hole here, the most force is going to be applied towards the center here where this blue arrow is. As you go closer towards the left and right sides, I'm going to draw a smaller arrow and smaller arrow. There's going to be less and less force, less and less force applied to that surface there. And that's just how bearing loads work, which is why we're going to apply that. So that's why we're not going to use a force, because the force is going to assume the entire surface is going to get an even pull of the of this force of whatever newtons we put in now. But we're going to change this to bearing load. I'm going to face this down. I was pointing up, and I'm going to zoom in a little bit more, but it's going to remain the same size. But as you can see, it's drawing arrows. It's representing it similar to what I just drew, which is the bigger arrows are in the middle there. It might be small to see on your screen. And then the smaller arrows are towards the edge, and there's no arrows pointing up either. So it's all going down with the most force around where my mouse is right there. So this is the best representation for this rope here. So we can go ahead and apply, let's go 50-pound force. And unfortunately, we can't just select each of these edges. I did that and it didn't work quite properly. It didn't calculate it well. So we have to do these manually, each one at a time, just for the best results here. So I'm going to go ahead and apply 50-pound loads or pounds force to each one of these, and then we'll calculate this. Go to this load again. Bearing load. Point it down. And then right click 12 o'clock for the same thing. Put it down. At 50. All right, we have our constraints. We have our loads. We're still using steel. We'll go ahead and generate context since these are two separate bodies there. We got the green check mark. So let's go ahead and solve that. All right, so this safety factor is actually getting close to breaking with if we were to have an optimal or a 50 pounds of force on each little face there. Let's take a look at the stress here. And again, this is exaggerated, but let's take a look at the stress. As you can see here, okay, yeah, most of the stress is happening over here, but there is some slight stress going on since as you remember the arrows, most of it should be in the center here. It's actually going to be a little bit more towards the left. It looks like because it's getting pulled inwards, the rope might be applying more stress onto that surface there. And as you can see on the top, there's a lot less over here. Oops. Same goes for the other side here. It looks like there's going to be a little bit more stress on the right side as opposed to the left side. And this is the actual deformation of the model, which is this middle guy here. And you can see this representation of how little it dropped. It is going down a little bit because it's bending a little bit, but it's not by much. So that's when I would apply a bearing load, is whenever there's a cylindrical face, and then there's gravity that's helping with the force of it, or it's being hung onto this, like some wires, for example. All right, let's go ahead and hop over to remote force or moment. So we're going to go back to this wall shelf example here. And remote force or moment is ideal when the object in space is represents as unimportant to model or is too difficult to model. For example, the effect of wind on a mast or force lifting a heavy object. So for example, I'm going to choose a different, I'm going to choose the same constraints here, but I'm going to choose a different load. Let's stop our force here. We'll stop using that one. And I'm going to go ahead and use the remote force. And let's pretend that I want to hang from this wall shelf, this steel wall shelf, and it's like a high above me, and I'm like about 200 pounds. But I don't want to draw my hand kind of onto the corner of this. Like, let's say I'm hanging from this corner. There's my hand. It's actually much bigger than this because this is like a not that big of a wall shelf. But let's say I don't want to draw that, right? So I will go ahead and create a remote force there instead to roughly represent where my hand would have been. Let me first actually show a force application here. So if I were to use this force onto this corner, I'll show you why it wouldn't work. And then we're to do the 200 pounds of force, because this is really quick to simulate, so I might as well show it. So this might be like an alternative to it that you might think of, but you can see it's way too specific to that point, so it might not be the best representation of the overall simulation there. So what we might want to do instead is the remote force. So let's go ahead and apply that. And this doesn't have to be on the model. It could be higher or lower. It's a representation of it. And we'll do the 200 again. And as you can see here, it's represented by a bigger blue dot there, and then there's a lot of little ones that go around this whole face. That's because think of them as like digital beams, if you will, that connect to all of them. So it will affect the rest of the faces as well, as opposed to maybe that one force that I applied to this vertice, it might not have affected it as the same. So maybe it's a better representation for the hand than just the corner there. So if we apply this, or if we solve this here, we might get we will get a different result than the corner force. And as you might guess, most of the stress is going to be onto this right side of the wall shelf. And you can see the bend there, and go ahead and animate that. So that would be a use case of remote force. I'm not going to show a moment because it's a very similar idea, but that was remote force and or moment. Next, we'll take a look at hydrostatic pressure, which is a very straightforward application here. So if we have this glass fish tank, we can go ahead and go to simulation. Once again, static simulation. The material should be glass. Looks like it's steel. So that's the only scenario where we'll make it a little different here to make it more realistic. Constraints, it's going to be held at the bottom there. And we want to simulate how how this thing will hold the water and where the most stresses will be. So if we apply the structural load here, we won't use pressure here because the hydrostatic pressure varies linearly from the level of fluid in the direction of increasing depth of the fluid. So that essentially means the higher or the deeper the water is, the more pressure there'll be towards the bottom of this. Hence why we need to turn on gravity, which it just yelled at me for. So let's go ahead and turn that on. And then we can go ahead and apply the targets this hydrostatic pressure will affect. So I'm going to select this interface here, holding the left mouse button, select that interface there, and I should have all 5 faces selected. Next, I would need to select the surface point. So this is, as you may guess, the surface, the top of the water. So we'll go ahead and fill it to the brim there, which is not a good idea because the fish you throw in a fish, it'll displace that much amount of water coming out. Okay, and no contacts need to be solved here. So we'll go ahead and just solve for it. And again, high factor of safety. This is adjusted. As you can see here, maybe the high and top parts of it might be more susceptible to stress there. And then you can see most of the stress from the water is actually towards the bottom here, towards the edges there, which is really interesting. And let me go ahead and animate this. It's always a good visualization tool. And let's go ahead and narrow this down to see where most of the stresses are being applied to this model. Also, I wanted to draw your attention to the different types of liquids. You can put in here seawater, fuel, oil, or you can put in a custom density for the liquid that you have. But it looks like we're just going to use water in this case. Last is a linear global load. So the linear global load is, think of it as just applying your own kind of gravity to this. So if we go to loads, and this isn't even in structural loads, this is right below it, angular and linear global loads. This is, imagine the whole model being affected. Like you're applying gravity to this model, maybe something like a bullet, like you're applying acceleration to a bullet for maybe something like event simulation, which is a different can of worms. So as you can see here, the window gives me the option to select a reference. It's assuming all the bodies in here is going to be affected by this linear global load already, but they just want a reference for the direction in which I want to apply this load. So if I'm going to select this face, for example, and I'll tell it 100 meters per second squared. And once I apply it there, as you can see, if I apply it to this face, or if a force was being applied to this face alone, this model probably wouldn't move at all because this is just fixed there. But if I go ahead and solve for this, since this is a linear global load, it's going to affect the entire model. And you can we'll see what it looks like. As you can see, it affected this part of the model as well. And that's because, again, it's towards the entire mass of the object. And if there's no mass in here, then it's not going to work at all. But so that's why it's bending here, because this is the only part that's fixed and everything else is susceptible to the acceleration that I applied to it. That's my best representation of explaining a linear global load. Do what you will with that, but I figured it'd be nice to at least mention in this segment. All right, now we can hop over to the fun stuff. Mesh best practices. So first, we'll talk about any bending materials. So let's go to the wall shelf as a prime example for everything here. So if you look at the mesh for this, let me turn on the first force we applied. If we count the mesh here, this is about one mesh. And if this thing is bending, which it is, we want it to have more than that. So this is after talking to our simulation experts, and they recommended having 2 to 3 different layers if we're bending with inside of the simulation workspace here. So one way to go about doing that is if we go up here to our settings, we can go to mesh, and we could lower the model base size to about 4%, 3% there. Right click on our mesh and generate the mesh again. And we'll see if it's going to be 2 to 3 here instead. So if we count here, 1 and then maybe 2. So that's better. This is better for it's going to give us a more accurate result at the end of the day that we calculated that. So that's one best practice I would recommend, that we would recommend. The next is when working with holes or cylindrical objects, you want about 16 to 24 elements that go around the circumference of this. So if we go back here, we coincidentally have a hole or cylindrical object here. And to get the best calculations, let's count this. This is 1, 2, 3, 4, 5, 6, 7, 8. What did I say? 16 to 24. So this isn't going to be enough. I don't want to give a whole bunch to the rest of the model. So what we're going to do here is add a local mesh control. That's by going here to manage local mesh control. And there's a lot of green dots and tools that we can use here. I'm just going to select this edge here, and I'm going to give it a length of 2 millimeters each. And let's go ahead and regenerate that and see what it gives us. 16 to 24 is what we're looking for. We can even compare it to the one here on the right-hand side. As you can tell, this is not as detailed as the one over here. So let's go ahead and count this one real quick. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. That's right in between 16 and 24. So that's perfect. Oops, sorry. So that's something that you'd rather get a closer number to calculate for around cylindrical objects. I just use that as an example. But that's another recommendation we would give you for that. Let's see the next one. So there's an image example. Leaving fillets where it matters. All right. So as you saw earlier in this example, let's go back to non-mesh. Okay, so we don't have any fillets here at all, but we actually should, because remember when there's a lot of stress there and we actually simplified this and we took out this green line there. We actually want to leave that in. That's because it's actually really critical to the overall end result of this, as you may guess. So instead of removing everything, let's go ahead and uncheck that fillet there. So that will remain in our calculations. Let me go ahead and solve for that. And you get the point. We could just hit solve and probably get a more accurate representation. And it might be even stronger because that fillet's actually really critical there. So that one's a more obvious one. A good workflow is to, where there's a larger stress gradient, you want finer meshes. So this one might be a little obvious as well. But where you have the most stresses, so let's go ahead and actually solve that so we can see the stress. But we actually want more meshes, more triangles to where most of the red is, if you will. So of course, it's going to be where that fillet is, right? So what we can do here, just like we did for the circular edge, we can go to local mesh control. We can select that face and make this 2 as well, and regenerate that mesh just to see it increase in triangles, which it did. And then we can go ahead and solve for that. So again, the end goal is to get this as realistic as possible. It's never going to be exactly what it will be like in real life, especially with like flaws to your materials and things like that. But we're trying to get close. Lastly, we don't have to calculate everything. So what's the point of solving for something if it's not really playing a big role in it? This is not the best example for that. Let's go to our line dry clothing hanger. We have a lot of material, a lot of meshes down below here that are included in our calculations. This part here, but it doesn't actually affect it too much because most of what's going on is right around here. So what we will do is we will get rid of that. So we can go to the simplify workspace to do that. I will offset a plane. I don't care how far, just roughly far enough there. And then we can go ahead and split the body, this body here, with that plane. So then we will not just hide it here, but we will actually right click and remove this. Oops, wrong one. Right click and remove this. So then when we go to calculate this, we go ahead and generate this mesh. I don't know if I did the context there, it will matter or not, but you can see that 1, 2, 3, 4, 5, 6, 7, like about 8 per line here. And we're going down. What I removed was like maybe 50 lines of triangles there. It doesn't have to calculate. We're already working with all these surfaces here, these triangles here. We don't need an extra 8 times 50, 400, 4,000, whatever, or triangles down below here to worry about. We'll just focus on what we're solving for, which is why this would be best practice, is to remove that with like a split body command or whatever situation scenario you have. All right, so I have some links here that I've already posted, these 2 links here in the chat room. I can post it again here just for those of you who came later, just so you can reference this. There's the structural loads, and then this is going to be the previous static simulation webinar, and then our Autodesk Virtual Academy. Go ahead and post the link to sign up for those. Those are our Thursday weekly webinars that we do for the rest of the Autodesk products in the collection. And here's our support line. If you have any technical issues, if you have support with us, we can definitely help you with that. Or if you have any questions, just reach out to us and we can decide from there. And go ahead and write down my email in case you need to contact me with any questions at a later time. So I'll go ahead and open it up for questions. I don't see any come in, but I see people in the crowd here. But I appreciate everyone's time. Thank you so much for taking time out of your Friday to join me on today's session. I know it went a little bit longer today, but I hope this was helpful to everyone. And this was pretty interesting for me to do. There's a lot of different theories and applications for this. that I did generically. We could definitely dive deeper if you request to see that. So hopefully this was helpful and somewhat relevant. There was it's about like 50% relevant to you guys that are using simulation. So I'll go ahead and wait another. Oh, there is a question actually that came in from YouTube. Oh, never mind. That was not a question. But someone chatted at YouTube. So yeah, you could definitely view this live on YouTube as well. Just as a reminder, in case you don't have the link for this, be subscribed to us on our KETIV YouTube channel. All right. With that said, thank you, Brian, for joining. Another Brian. I'm not thanking myself there. But thank you all for joining, and everyone have a great weekend or Thanksgiving if I don't talk to you till then. Take care, everyone.